The last basic preemptive scheduling algorithm that we are going to work with today is round robin. So round robin is preemptive by necessity. The basic idea is that each process is only going to get a very short amount of CPU time in terms of a quantum. This is typically somewhere between 10 to 100 milliseconds, but it can be shorter than that. And after this time has elapsed, that process is going to be taken off the CPU or preempted, and it'll be added to the end of the ready queue. When that time quantum is large, this does result in a first come, first serve scheduling algorithm instead. But when that time quantum is very small, we typically result in having the overhead related to the context switches or the dispatch latency become too large. If the overhead is too large, we are overall reducing the CPU utilization in terms of the amount of work that can be done. So as a general rule, we would want there to be about 80% of CPU bursts that could finish within their first quantum. But there is a limit in this algorithm for how long any given process is going to have to wait. And that is limited to n-1 times q. So that's n being the total number of processes that are in the system. And we don't have to wait for ourselves. So that's how we get the n-1. And then each process is going to be executing on the CPU for at most q milliseconds or time units. So that is how we get that n-1 times q. When we work with round robin, the amount of processes that will get to run within a fixed time frame typically matters, and so does the number of context switches. So as an example, if we have a time quantum of 12, if we are estimating this within a window of 10 milliseconds, maybe only one process actually runs during that time, with 0 context switches. If we have one context switch in a time quantum of 6, we can get 2 processes to run during that 10 millisecond time. But if we're switching every millisecond, which is what a time quantum of 1 would mean, then we are performing approximately 9 context switches within that 10 millisecond frame. And suddenly we have high overhead and it matters. So this is one of the reasons why we pay attention to right-sizing our time quantum for the round robin algorithm. So let's look at an example that has a time quantum of 4. This particular example is the one that we used first with first come, first serve. So we have process 1 with a burst time of 24. Process 2 has a burst time of 3, and process 3 has a burst time of 3. Now, when we are working with a Gantt chart for this, again, we're preemptive. So the number of boxes is going to be greater than the number of processes, most likely. We're going to start with process 1, let it execute for a total of 4 time units. Then process 2 will take over, and it has a total of 4 time units to use, but at time 7, it's actually done. So this is going to be a non-preemptive scheduling decision at that point in time, which is going to get process 3 onto the CPU. Process 3 has 4 milliseconds in order to execute, but it only needs 3. So then at time 10, it's going to voluntarily give up the CPU and let process 1 back on. Now at that point in time, process 1 has a total of 20 milliseconds of CPU burst time left. But even though it's the only process in the system, round robin means that it's going to check every 4 milliseconds. So every 4 milliseconds after time 10, we have an unnecessary context switch that is going to take process 1 off of the CPU, make a scheduling decision, and then put process 1 back onto the CPU. And that's because it's entirely possible that other processes could have arrived during that point in time and need to have their own turn on the CPU. So this does typically have a higher average turnaround time than the shortest job first, but the time it takes to get that first response from a process is better. So this works better for interactive processes. You would think that there would be some way to have the time quantum directly impact the average turnaround time, but we find that it's pretty jerky until we get to a point where the time quantum is larger than 80% of our CPU bursts. So here, when we get to a CPU burst of time 6, we are now greater than or equal to 3 of the 4 processes. It results in a lower stable average turnaround time.